Welcome back. In this lecture, we're going to be looking at an important application of probability, and that application is screening tests. Now, screening tests are important real-world applications of conditional probability. Screening tests are decision-making tools that incorporate both prior information, information from some population of interest, and new information about specific individuals from that population. Now, these two types of information are combined using Bayes' theorem. Now, here's an outline of the topics that we'll be discussing. The first topic, possible screening test results. We'll then look at population rates associated with those results. We'll look at how to characterize the accuracy of screening tests. We'll also look at how to characterize disease in the population. We'll then look at how to properly interpret results from a screening test. We'll then look at a sequential two-stage screening test. And then in subsequent videos, we'll look at some applications of screening tests, in particular random drug testing and pap smear screening test for cervical cancer. Now, screening tests are useful in checking for the presence of a disease, a chemical compound, and in general, really any characteristic or condition of interest. Now, for ease of presentation, the following terms that we're going to be defining associated with screening tests will be defined in terms of disease. To state the definitions in a fully general way, the word disease could be replaced by characteristic, for example, and the words person and persons could be replaced by the words experimental unit and units, respectively, but that gets a little cumbersome, and so we will define these terms and discuss them in terms of disease and people. Now let's first look at possible screening test results. So a true positive occurs when a diseased person tests positive. A false positive occurs when a non-diseased person tests positive. A true negative occurs when a non-diseased person tests negative. And finally, a false negative occurs when a diseased person tests negative. Now, we can organize these definitions in a two-way table that may help us to better visualize these four possibilities and to remember what they mean. So the columns in this table correspond to the reality about the disease. Is the disease present or is the disease not present? And then the rows correspond to the result of the screening test. So is the screening test positive for disease, or is the screening test negative for disease? Now, if the person has the disease and the screening test comes back positive, that is a true positive. If the disease is present, but the screening test comes back negative, that is a false negative. If the disease is absent, but the screening test is positive, that is a false positive. And if the disease is absent and the screening test comes back negative, that is a true negative. Next, let's look at population rates associated with these outcomes. So the true positive rate is the proportion of diseased people who test positive. The false positive rate is the proportion of people in the proportion of non-diseased people in the population who test positive. The true negative rate is the proportion of non-diseased people who test negative. And finally, the false negative rate is the proportion of diseased people who test negative. Now let's look at the relationships between these rates. The true positive rate and the false negative rate will always add up to 1. Similarly, the true negative rate and the false positive rate will also always add up to 1. So these are some relationships between these 4 rates that are useful to remember. All right, next, let's look at how to characterize the accuracy of screening tests. Now, there are 2 aspects comprising the accuracy of a screening test. These 2 aspects are called the sensitivity of the test and the specificity of the test. The sensitivity of the test is the conditional probability that a diseased person tests positive for the disease. It is a measure of the ability of the screening test to correctly identify those who have the disease. It is numerically equal to the true positive rate. The specificity is the conditional probability that a non-diseased person tests negative for the disease. So we see here notationally the conditional probability that a person tests negative given that they do not have the disease. The specificity is a measure of the ability of the screening test to correctly identify those who do not have the disease. And the specificity is numerically equal to the true negative rate. So those are the 2 aspects associated with the accuracy of a screening test. Next, let's look at characterizing disease in the population. That is given by the prevalence. Now, the prevalence is a quantity that must be known in order to properly interpret the results of a screening test. The prevalence of disease in the population of interest is equal to the proportion of people in the population that have the disease that is being tested for. Now, when a person is selected at random from the target population, then the unconditional probability of selecting a person with the disease, which is denoted as shown here, the probability of disease, is equal to the prevalence. So again, the prevalence of disease in the population is the proportion of people in the population that have the disease being tested for. And when we select a person at random from that population, the unconditional probability of selecting a person with the disease is equal to the prevalence. All right, now let's look at how to properly interpret the results of screening tests. And to do this, we have to combine information about the population along with the results of a screening test itself. There are 2 values used to interpret the result of a screening test. The first is called the positive predictive value, or the PPV, and the second is the negative predictive value, or NPV. The Bayes Theorem can be used to calculate both the PPV, the positive predictive value, and the NPV, the negative predictive value, from the sensitivity and specificity of the screening test, along with the prevalence of disease in the population. And so the PPV and the NPV are calculated using Bayes' theorem by combining information from the population, that is the prevalence, with the results from a screening test where the sensitivity and specificity of the screening test are known. Now, the positive predictive value, the PPV, is the proportion of those testing positive that do have the disease. Now, stated in terms of probability, the PPV, the positive predictive value, is the conditional probability that a randomly selected person has the disease given that they tested positive. In other words, the PPV, and you can see the notation there, it's the conditional probability that the person does have the disease, given that they test positive. Now, the PPV and the sensitivity are different values. All right? We've seen here that the PPV is the conditional probability that a person has the disease given that they test positive. On the other hand, the sensitivity is the conditional probability that the person tests positive given that they have the disease. And so while both of these are conditional probabilities, they are different conditional probabilities. In the PPV, we're conditioning on the test being positive. In the sensitivity, we're conditioning on the person having the disease. So these are completely different conditional probabilities. And so we see here that the PPV is not equal to the sensitivity. Those are two different measures, two different values, two different conditional probabilities, and so we don't want to confuse those. Now, we can calculate the PPV using the sensitivity of the screening test, the specificity of the screening test, and the prevalence of disease in the population of interest. And we get this formula by applying Bayes' theorem. And so we see here that the PPV, the positive predictive value, is equal to the ratio of the product of the prevalence of disease in the population with the sensitivity of the test to this more involved quantity in the denominator, which is the prevalence times the sensitivity, plus the product of 1 minus the prevalence and 1 minus the specificity. Now, the negative predictive value, the NPV, is the proportion of those testing negative that do not have the disease. Expressed in terms of conditional probability, the negative predictive value is the conditional probability that a randomly selected person does not have the disease given that they test negative. And so we see that notationally down below. The NPV is equal to the probability, and this is a conditional probability, that the person does not have the disease given that their screening test came back negative. Now, the NPV, the negative predictive value, is not the same as the specificity. The NPV is the conditional probability that a person does not have the disease given that their test came back negative. On the other hand, the specificity is the conditional probability that the person will test negative given that they do not have the disease. And so, similar to what we saw before, these are different conditional probabilities, and so they are not the same values. They don't represent the same thing. All right, so the NPV is not the same as the specificity. Now, Bayes' theorem can be used to come up with a formula for the negative predictive value in terms of the prevalence of disease in the population and then the sensitivity and specificity of the screening test. All right, so the NPV is equal to 1 minus the prevalence multiplied by the specificity of the screening test. That's in the numerator of this ratio. And in the denominator, we have that same quantity, 1 minus the prevalence times the specificity of the screening test, and then to that we add the product of the prevalence and 1 minus the sensitivity. Now, let's look and see how these quantities, the positive predictive value and the negative predictive value, depend on the prevalence of disease for fixed values of sensitivity and specificity. So, in other words, for a fixed screening test, so if we have a particular screening test, it's going to have a value for the sensitivity, it's going to have a value for the specificity. And so, how does the positive predictive value for that test depend on the prevalence? Well, if you look at the expression for the positive predictive value and you analyze it a little bit, you'll see that the positive predictive value is an increasing function of the prevalence of disease in the population. Now, what does that mean? That means that for given values of sensitivity and specificity, in other words, for a given test, the positive predictive value will be lower in populations with low disease prevalence, and it will be higher in populations with high disease prevalence. Now, here's a graphical illustration of what I'm talking about. This is the positive predictive value as a function of prevalence for a particular screening test that has a sensitivity of 0.95 and also a specificity of 0.95. And so we can see here that when the prevalence is low, when the prevalence is close to zero, then the positive predictive value is also close to zero. But as the prevalence begins to increase, as it gets larger, we can see that there's, at least in this graph, a rather sharp increase in the positive predictive value. As the prevalence continues to increase, the rate of increase of the positive predictive value diminishes. All right, but we see here in this demonstration or illustration that the positive predictive value is an increasing function of the prevalence of disease in the population. So as the prevalence increases, as we move to the right on that horizontal axis, then the positive predictive value increases as well. And so what's the interpretation? How can we use this? Well, if somebody is being tested for a particular disease, and that disease has a very low prevalence in the particular population that that person belongs to, then, for example, for a test that has a sensitivity and specificity of both 0.95, which seems to be a pretty accurate test, the positive predictive value may still be rather low. In other words, the probability that the person actually has the disease, given that their test came back positive, may be fairly low. It may only be 10% or 20%. On the other hand, if the prevalence of the disease in that particular population, is 0.3 or above, in this graph at least, then there may be a much higher probability that the person has the disease, given that their test came back positive. Now, the NPV, the negative predictive value, is a decreasing function of the prevalence of disease in the population. And so what this means is that for given values of sensitivity and specificity, the negative predictive value will be higher in populations with low disease prevalence, and it will be lower in populations with high disease prevalence. Now remember, the NPV is the conditional probability that a person does not have the disease given that their test came back negative. And so here's a graph of the NPV as a function of prevalence, again for a screening test that has a sensitivity of 0.95 and a specificity of 0.95. And we see here that the NPV is a decreasing function of prevalence. As the prevalence increases, as we move to the right on that horizontal axis, the NPV decreases. It decreases slowly at first. Then, once we get to about 0.7, it really starts to decrease rapidly. Now let's look at what's called a sequential two-stage screening test. Consider a two-stage screening test procedure in which the second test is administered only if the first test is positive. So what we have in mind here is an overall screening testing procedure that involves two individual separate tests. If the first test is negative, then the second test is not done. All right, and the conclusion would be that the person does not have the disease. If the first test is positive, then the second test is going to be administered, and then we're going to see what the result of that test is. So in this two-stage test, it will be considered positive if both tests are positive and negative if either of the two tests is negative. So if the first test is negative, we proceed no further. We conclude that the person does not have the disease. If the first test is positive, but the second test is negative, then again, we conclude that the person does not have the disease that's being tested for. So that is how this particular two-stage screening test works. Now we want to derive the sensitivity and the specificity for this sequential two-stage screening test. And the sensitivity and specificity for this two-stage test is going to depend on the sensitivity and specificity values for the two individual tests. And so let sensitivity 1 and specificity 1 be the sensitivity and specificity of the first test. Let sensitivity 2 and specificity 2 be the sensitivity and specificity of the second test. Now, as long as the tests are independent of each other, conditional on the true disease status. All right, let me say that again. As long as the tests are, we could say, conditionally independent. In other words, independent of one another, conditional on the true disease status. Then the formulas on the next slide give the overall sensitivity and overall specificity of the sequential two-stage test. And so the overall sensitivity of the sequential two-stage screening test will be equal to the product of the sensitivity of the first test and the sensitivity of the second test. The overall specificity of this sequential two-stage screening test will be equal to the specificity of the first test plus the specificity of the second test minus the product of the specificities of the two tests. So this is how we can come up with the overall sensitivity and the overall specificity for the sequential two-stage screening test. Now notice that because the overall sensitivity is the product of the sensitivity of the first test and the sensitivity of the second test, and because those sensitivity values are less than 1, the overall sensitivity of the sequential two-stage screening test will be no more than the minimum sensitivities of the two individual tests. In fact, it will be less than the sensitivities of both individual tests. All right, so that is the end of this particular video. We'll look at applications of screening tests in the next lecture video.